Why? For those people on Zoom, can you guys hear me?
Yes.
Okay, yeah. Don't know why the audio is not going, but like, sure, I can hear you. That's the most important thing. All right. So, oh, there we go. It's probably because of the internet. That's fine. You can find it. You can find it after. Right. So, week 5, Thursday, the day before the stress day. But like, anyways, yeah. I mean, yeah. Like, we'll have all those pieces too. Some announcement. Whoa. What is going on? What is this? But anyways, I guess this is fine. So office hours. There's no change in office hours. So please keep coming to office hours. So we can have a, I don't know, maybe angry conversation or discussion about stuff. Yeah, maybe we could fight over that. No, just joking. But anyways, and also for the homework that's due next week, due on next Tuesday, we have an optional problem that's called random walk. Please do that problem if you really have time. It's not too big of a deal, but because we're gonna have another problem in the future that's related to this one. So maybe you can reuse our code or whatever. Okay. So, and also I spent the entire afternoon figuring out how that works. So do it. Yeah. It's not that bad. Like it really is not that bad. Also, if you have trouble understanding what a random walk is, come to office hours tomorrow or like this afternoon. Emily's not here, but yeah, come to like the office hours. Attendance forms over here. This link is updated. Sorry, I didn't renew it, but yeah, just scan the QR code. That's new. All right, recap. Anything regarding logistics? Any questions? All right, yeah, do the random walk question. Okay, so yeah, this is the first question. Let's do some recap then. We're not gonna be doing a lot of plotting today, but it's kind of important as well. So like, what are some arguments or parameters that goes into this PLT.plot thing? Anyone? Yeah, that's useless.
You can put in a kind of like dots or dashes or however you want the plot to show up.
Sure. Colors. Yeah. What else?
You put a marker in. A marker, like you want to put like a.
There are several things related to markers, though.
Okay, well I don't know. You can get a star.
Oh, okay, marker style. Yeah.
You can get a, what's it called? Legend.
Legend doesn't go into this. It's called label in it. Legend is another thing. It's another so you can label. I see what you mean, but like there's no such parameter called legend under PLT.plot.
What's the difference between a label and a legend?
Well, I mean like the parameter, the name of the parameter, you can just put legend in it. It's the same thing. Yeah, it is the same thing. Yeah. All right. Yeah, that's why we're astronomers. We got the best plots. Yeah. So yeah, what other plots can you do? Like other than like PLT.plot and PLT.scatter? Those are the two basic ones. What else? Histograms. Mesh grid. Yeah, that's it's a 2D plot basically. 2D density plot. Yeah. What?
You can plot images.
Yeah, you can plot images. Anything else? That's pretty much all actually. Yeah. Yeah, but plotting in science, right? Plotting is just a way to show your data, to show what you have, what you observed. But you have to, another important thing in your in science is to how to interpret the data. When you write your lab report, you have like this method and then this result, right? After result, you have this stupid discussion section, yeah, which is always the hardest to write. Besides introduction, sorry, let me just close the door. Yeah, right. So if I just simply have some data, right? If I just simply have some data like this and then without the dashed line, what does it represent, right? No one knows. How do you interpret them, right? So you can fit the data on that. I think most of you may have known already. Have you done this in, I don't know, like in some of the lab classes, or maybe for you in high school, I guess. Yeah. And then you can fit all the dots basically. Each one's called a data point with a curve. Well, this is a straight line, but it's just a special case for a curve. So yeah. Yeah, and then one of the ways to know the correlation between the x and y variables on the two parameters, or even more, and basically to know the trend or what specific functional form the two variables follow, right? And statistical insight, who cares? Yeah, those are the hard part. Yeah. So this is what we need for fitting, right? One of them is data, which is what we have over here. This ugly plot that I made actually. Yeah, that was I think a day before this lecture was presented a year ago. But, yeah. And the model as well, like some functional. Like I don't know what this is.Maybe this is a sine, this is a cosine, or some sine squared with a shift. Who knows, right? But it's some functional form. Y is a f of x, right? Any questions so far? It's not sine squared, right? Who knows? I scaled it, maybe. Maybe with some shifting factor. Yeah. Yeah, I don't know. I plotted this a year ago, so who cares? Yeah, so there are several models that you can apply. The simplest one in science is a polynomial, right? The even simpler one is a who cares? Yeah, a polynomial in the mathematical form is just written over there: a0 plus a1x plus a2x squared, etc., all the way to a of n times x of n, right? Which you can write as a sum. But normally though, you don't have to write out something like that because it's just too complicated. So there's this thing called numpy.polyfit. See, numpy is useful. Numpy.polyfit, it automatically fits your data with a polynomial. With you be specific about the degree of the polynomial, which is the highest order of the polynomial, right? So say for example, if you have x squared plus 2x plus 1, then the degree of the polynomial is going to be 2. If your leading order term, which is the term with the highest order, is x to the 10, then this degree would be 10. I don't know why you would fit that, but like yeah. Yeah, and then this, if you run this, it gives you a whole bunch of coefficients over here, right? Which are each of these coefficients in the sum, which is AI, starting with the lowest, highest order. Any questions? Good, that's good. Right. So, well, I mean, this is always this should always be the first one to try when you're actually fitting a data, right? And another thing is on the slide. I think I was actually taking a course on this. It's called overfitting. If you only have like 5 points, don't fit it with a degree 10 polynomial because it's definitely gonna fit. Okay. So if you have 5 points, start with the lowest, like maybe a straight line, maybe a second order, maybe a third order. When it go up to 5, and if your fit goes really well, then you have to be a little bit suspicious about that. Okay, be careful. Yes. You can just put a number over there. You can also put degree equals something. That's fine. Yeah. But normally that's just the order it works. So x data goes first. Y. So x is your independent variable. Y is your dependent variable, and then you put the degree of a polynomial that you want to fit on. Yeah. The overfitting thing, I think you'll have to worry about that like in this class, but you will do when you actually do labs, especially upper division labs, right? Questions? If no, we'll just keep going. Great. There we go. I'll click on this. this is a good fit. The way we define a good fit is first by eyeballing if the fit actually matches our data. That's normally the most trustworthy way. No, it's okay. So there's a mathematical way to do this, which is to minimize this thing called chi-square, which is super weird. There are multiple ways to define chi-square. There's only one way, which is essentially you can see this is your original y data, and then this is your fitted model. So let me draw it actually. Maybe actually better. So say this is some curve, and then my data points, I don't know, are like this. All right, and then this yi is just this value, like the y position of each point. But the f of xi is the corresponding x, but on the curve. So it's this y value. Does that make sense? It's a different. It's essentially the vertical difference between the point and the curve. And then you square them, sum them up. But this uncertainty thing, it could be or could not be there. It's fine. Who cares? There's too much detail in it. And then you square it, and then you're done. If this thing is minimized, then you have a good fit, right? Questions? You can write this thing if you know matrix multiplication, but we're not going to do this in this class. Yeah.
Like what would be good chi-square?
It's the one that minimizes the thing. Depending on what kind of chi-squares you're talking about, I think. There's one way, that's one of the chi-square, I think you want to minimize it to make it as close to 1 as possible. Yeah, but if it's just there is one to that you want to minimize it up down to 0, and that's basically just taking the difference without the uncertainty, because the best fit is when the points are right on the lines, right? Yeah, there are multiple ways. I've got like chi-square of, I don't know, 9,000. Yeah. But yeah, and it's a good fit. Yeah, and also the overfitting thing that I was talking about. Yeah, so your number of data points should be much larger than the number of fitted parameters, right? So I use the example of a polynomial. And that means if you have 5 points, don't fit it with a 10-degree polynomial because you need to fit 10 coefficients. But that also works for other functional forms as well. You can have a whole bunch of parameters in a function, right? Does that make sense? Got a question, Nick? Oh, okay, yeah.
Is there like in the map, like what would the import the map?
Import what? Math? Or
Yeah.
math?
Map.
Yeah.
Is there like a sigma function that's already in the text? I don't know.
Well, depending on what sigma you're talking about, like this is just the uncertainty of your measurement. This could come from your own experiment. It doesn't come from like some explicit calculation that you do with your data. This is part of your data. Yeah. So when you take a point, like a single data point without any uncertainty error bars, it doesn't make sense much, right? So yeah, that's what the sigma is. If you're talking about like standard deviation, that's in NumPy, right? NumPy.std. Then you calculate standard deviation of a sample. Yeah. All right. Yeah, some more complicated functions. I just talked about polynomials. But what if, let's say, for example, this function over here, this is an exponential, right? Then NumPy.Polyfit doesn't really work. What it works because you can essentially write all the functions as some polynomials, right? But but yeah, but if you just know, like my model is some exponential, I don't have to fit a polynomial anymore. I can just use, I can write a model that's an exponential, fit it to that, and then that involves another package which is called SciPy the optimize.curvefit. So to import a package, you import this thing, this curvefit function from SciPy to optimize. And then, yeah, who cares this? Oh, that's just a note. The note is saying, I could technically just import SciPy, and then when I call this curve fit function, I do SciPy.optimize.curve fit. Yeah, but that's too long. Don't have the energy to do that again. You can just literally import a single function, and just call it directly without actually using it. It saves you a lot of time actually. Because SciPy is a huge package. You don't want to import it all at once. Yep. Okay, let's just put this here. Okay, there we go. Yeah, so curve fit gives you a fitting parameter, basically like all the parameters that you're fitting. Say for example, I have the exponential. Like say my model is like amplitude, like some constant times the exponential times some other constant, something like this. Does that make sense? And then I'm trying to figure out, I know it's an exponential, but I need to figure out what A, B, C's are. Okay. So those are the fitting parameters. So that's why what we call the fit params. You don't have to do that variable. You don't have to follow the same way that we name our variables. And then just call curve fit. And then there are three most important things that go into curve fit. First, your model. In this case, the exponential. Second, your x data. Then your y data. Okay. And then there are three more parameters that goes into this function. First one, normally you have to have it. This is called P0, which is your initial guess. So you look at your data, you stare at your data, trying to guess what ABC are. Like just guess, make a wild guess, because this function is very initial condition sensitive, which means if you tune this to a value that's totally different from the actual value, what's going on? The actual value, then it might not work. Like the function might not work. Just gives an error or like says it's not good fit. It's not a good fit. So you have to give it an initial guess. And then uncertainty, sigma is the uncertainty on y data that comes from a measurement. You don't really have to put it over there if you don't have the uncertainty. That's fine. Same thing for the bounds. So because if you know that A is some number between 0 and 1, you can just restrict it in the bound, saying 0 and 1. This is lower bound, this is upper bound. All of these are on Google. You guys should go look at it. Yeah, because running from like 0, say if you know A is from 0 to 1, but like this Python thing runs from 0 to 100, then you might be a little bit off. Okay, and then your function may not be working. Yeah, and then this is just an array. X and Y data are just arrays. But model is actually a function. And the function, the arguments, these variables in the function, the first one, it has to be the independent variable. Okay, that has to be the independent variable. And then all the other ones after that, those are the fitted parameters. Okay. And then you just return the functional form. In that case, I use the same example as before. This is like some sign, and you're fitting A1, A2, and A3. Does that make sense? All right. Any questions? Yeah, and then this thing gives you two outputs. Call the 0th one. Okay, don't call the entire thing. Because the second output is it's the uncertainty basically. It's uncertainty of the of your fit. So, but if you just want to fit, you can just take the 0th value. All right? Yeah.
Is there any just
what?
Are there any outputs after that, or is it just?
Oh no, they're just the truth. Yeah, they're just the truth. Yeah, but the second one normally is a matrix. Yeah. All right. Those are all that we're going to be talking about fitting data. And now we find roots of some functions because there are function forms that you can just solve by hand, like that. We can solve that like by hand. By hand or boba or boba. Yeah, or like you pass the class straight away. Can you actually solve that? No, you can't. All right, yeah. So there are equations in physics, and even in like some of your fitting models, like you find a zero. You want to find a zero, but you can solve it by hand. How do you do that? Like, then we have to use some computer to numerically solve the equation. So another way to do this is use from scipy.optimize, and then you import this thing called root, or yeah, you just find the root of that equation, and the solution. Okay, here comes the solution. You just call the root, and then you give the function, which is that equation, and then your initial guess. This is very important. You need the initial guess for the thing to work. Okay. And then you have your function, your model, this equation that you're solving is not going to be that. Because what root does is that it's finding the zero that's the zeros in this equation. So you have to move one of them onto the other side. So if you see over here, this function is actually defined as the square root of 1 minus x squared minus sine x. So and then you set that equal to 0. Then you find a root of that equation, which is equivalent to finding the solutions to the equation on the top. Yeah, makes sense. All right, and then you can just obtain a solution by calling your solution, or in this case, sol dot x, and then you will have all your solutions. Great. Does that make sense or not? Yes. Oh yeah. So if you have two curves, say for example, this is my first curve, add another curve, something like this, right? You want to find this point, and then you look at your data. You can plot them. Actually, you can plot them, or you can actually try some numbers, see which one is the closest, gives you the closest value, and then you find the x-intercept. This is your initial guess. Like maybe this is like 3 or something, right? And then put it in, and then it may give you like a more accurate result, right? Maybe it's 4, who knows, right? Maybe it's 3.523, maybe it's pi, right? So you can try to make that as close as possible. Just try it, or you can plot it. And that's fine, yeah. Because this only gives you a very rough answer by just eyeballing where the solutions are. But that gives you the precise answer. Yeah, more accurate answer. That makes sense? Yes.
So what did you say happens if we put the guess like something that's completely off? Like
no.
Guess it was 0.
Oh, like sometimes if the solution to this equation is 1,000 and you put initial guess as 0, like your solver might not work.
What would it return?
What?
What would it return?
Some really small numbers sometimes, or like your initial guess straight away. Yeah.
Why would it return some really small?
What?
What would cause it? What property would cause it to return?
No idea. I don't know how the thing internally works. Yeah.
So you're talking about initial guesses, right? How like
Yeah.
So like I guess the best way I can explain it to you is it's scouring a lot of like parameters to like minimize some values to find the proper root. It's not super important as to exactly what it's doing, but I'd like to just picture kind of like a trampoline, and that trampoline might have like dips in it or warps in it, and you're trying to find the deepest dip on the trampoline. I guess maybe a map, like a topographical map might be a better example. But if you give it a wrong guess that's like really, really wrong, there might be like a small minimum that it falls into that's not the actual global minimum, and that is what leads to a wrong answer. So giving a decent guess, or as long as it's not like the guess is negative and the value is supposed to be a positive, then you should be fine. But yeah, making sure you're in the right ballpark.
I remember in my high school, the calculus class, we actually did this thing called Newton's method of numerical finding the roots or something like that. I can't remember. They were basically using this this tangent line to find the root of the equation. And then there are only a finite of iterations that this thing is going on the backstage. So if like within like, I don't know, like a million iteration, you're not getting a correct answer, that's just gonna give you whatever that final one. That's one of the way. I don't know how this root function internally works though. If you write your own server, your own solver, you could maybe try to figure it out. Yeah, that's actually what's required for some of the labs. Yeah. Yeah. Also, there's this thing called solve as well, which functions exactly the same as the oh, stop. As root. Sorry. Yeah. There's exactly the same as root. You give a function. And then you give an initial guess over there. And then args. Good. Args. I don't remember what exactly they are, but from the best of my memory, they are, if you have multiple variables in say if you want to fix a in your function, right? So if you want to fix a in your function, you put like a equals something over there. Yeah. And then it's only gonna fit B and C. Or the other way around. I think it's the way that I just talked about it. I only used it once. Yeah. And don't care about this. No one cares about this because we're reusing all our slides. Yeah. Ah, there you go. See? Yeah. Yeah, I just talked about all of that. And the output is the same as the as roots as well. Yeah. All right. So have you guys downloaded data file, the TXT file from B courses? All right, let's do some public coding to embarrass myself. All right. Let's do that. So do you guys know how to open up a TXT file in NumPy or in Python? Great. Oh, no.
That was too much.
Yeah, that was too much. I mean, I can't move. What? All right. Is that good enough? Is that good enough? Yeah, I don't know why it's in French. I lived in Geneva, so like we spoke French there. So yeah. All right. So the file. So there are two there are two packages that you normally have to import all the time. The plotting one and NumPy. All right. And then this is very important because a lot of data actually comes in TXT file. So one of the ways to open it up, one of the fastest ways actually, that I think, is numpy.load.txt. And what goes in is the file name. Right? I'm not saving it, I'm just calling it. And remember a few weeks ago, I said 2D arrays are your best friend. There they are. It's a 2D array. All right. So let's just call this data. Actually, no, I'm going to call it X and Y. And then if I call X, it's a single array over here. Same thing if I call Y. All right. Questions?
The X, Y.
X
Created your spot.
What?
That created your 2D array when you put the X.
Yeah, so numpy.load.txt, this entire thing is a 2D array, but I can assign each element of that array as a variable in one line. You could also do like x equals this thing and then 0,
Yeah.
and then y equals this thing 1. It's the same thing. Yeah, it's the same thing. All right. So someone please plot this thing and tell me what shape it is. Yeah, I have notes over here just so I don't embarrass myself, you know.
You have to show it, or how did you get it? No, it doesn't exactly.
If you call x, print and call are different. Printing and calling are different. Printing, you're actually showing the
Oh,
thing.
you just type that.
Yeah, I just typed that over here. Yeah. Okay, did you plot it? What shape it is?
I'm gonna see what you did.
Does anyone know what it is? All right, so this thing. This thing is something like this. This is what we call a Plunge function. Yeah. Oh, why is it? Sorry. Let me zoom out a little bit more. Actually, can you still see it? Maybe not. Okay. This is a Plunge function. What is a Plunge function? Does anyone know? Yeah. So when a gas is in local thermodynamic equilibrium, they miss a line according to this function over here. Okay. So this is essentially the base of a stellar spectrum, right? So this function, here's some physics that I'm gonna tell you. You don't have to know this. I'll tell you all the functional form, but you have to type it in. Plunge function on this end is called intensity. This stupid thing has units of energy per second, per frequency. Wait, per solid angle, per area squared. Yeah. Or per wavelength squared. Oh, well, per wavelength, sorry. But anyways, on this side, it's just the frequency of your light. Light is an electromagnetic wave, has some frequency. Right. Wow. Don't say that. I'm sorry, but I've talked to people who don't believe that. And then for some gas or like your star, your spectrum looks like this. It's a spectrum just like how much light some object emits in certain frequency or energy, frequency or wavelength, right? Make sense? And this thing has a really weird form. This thing is a function of frequency and temperature, and then it has the form of 2h nu cubed divided by c squared times the exponential of h nu over kt minus 1 over 1. Yeah. All right. Now it's your job to put this in. Like write it into a function. Yeah. But I'm gonna tell you some like what those numbers are. So h here it is h. I don't remember the number. Yeah. So h is 6.6 times 10 to the negative 27. Speed of light is 3 times 10 to the 10 centimeters per second. And k is what we call the Boltzmann constant. You don't have to know what this means, okay? K is on the Boltzmann constant. It has the value of 1.38 times e to the negative 16 ergs per Kelvin in CGS units. All right, now it's your turn to actually let's define the temperature as well. Let's use the temperature of the sun. What's the temperature of the sun on the surface?
5 degrees.
5,000 K? Almost, yeah. 5,700. Yeah. All right, so let's define some Planck function, right? Do you guys have to follow me on this? Yeah, let's just call this new, and then we can just do return times 2 times h times new. Actually divide exponent of h times new times k divided by t minus 1. Okay, there we go. Yeah. All right. You can see that. Here's your function. New is what goes in the variable. Yes, that's the variable of the function that you're doing.
And you can have all the numbers in. You don't have to load any.
No.
And then that little e, it just works like that. No problem.
But then our goal here is to find the temperature of this the star, say for example, right? We have a star. We take the spectrum that looks like this. And then so this thing changes as temperature changes. As temperature goes higher, like your Plunge function goes like that. As the temperature goes lower, this function goes like that. Okay. So we want to find the temperature of this thing. Yeah. What? Sure. Yeah. So I'm actually missing something in this function. What am I missing? I predefined the temperature. Let's get rid of it. Let's add another variable. So this is the actual. You can literally using this function to plot any Planck spectrum. And then, oh, now here it is. We'll just run it. This is fine. We'll just run it. Want to figure out the temperature. How do we do that? Want to figure out the temperature.
Attempt to isolate temperature and then call the variable.
What do you mean?
Just solve it.
No. Okay. So
I write a version that takes that.
sorry, I can't hear you.
Isolate temperature. Isolate the rest of it to T and then call T.
Sure. But then that's a way. That's a way. Sure. How do you get temperature from this thing? That's your data. You don't know what temperature is. Like what you're describing is analytically how do you solve temperature as this? Sure. I mean, you can feel free. Yeah. What? Assign the x and y, and then use what? Yeah. What do we need to do? Fit it.
Literally a curve and then return that exponent like the power of the.
Yeah, something like that. This is your model. You have a model. You have a model over here. Like you know the spectrum. Oh, it's not here anymore. But like your spectrum is Planckian, right? So you can just solve it, right? I mean, we even defined this model over here, right? So we can just do we have x data, we have y data, right? We have these things. We can do it. So let's just do what's the function to fit the data? Yeah, just like not curve fit. Yeah, that's the one. Yeah, sure. SciPy optimize. Yeah. Yeah, here we go. There we go. We got a curve fit. What goes into curve fit?
You need your model X1 data.
Yeah. So curve fit gives you have x, you have y, which I think I just defined as x and y, right? Yes. You have x and y, and then what else? We need a model. Where it is? Yeah, it goes here. Planck. What else? Yeah, take a wild guess what temperature this is. 5,000. Sure. Yeah. Let's do that. Yeah. 5,000, and then we run it. See? It gives you, like I said, This thing gives you two variables. Where's the stick? Oh, there you go. Yeah. So here, right? So the new is just an independent variable. T is a fitting parameter, which we're gonna find from our data. So when we actually fit the data, it gives you two outputs, like I said before. First one is your parameter, fitted parameter. In this case, it's 5,708. And the other one is the uncertainty. Okay. Let me just tell you, like when I created that data, it was 5,700, exactly 5,700 help, which is not that bad, not far off from this one at all, right? But say, if we say instead of 5,000 Kelvin, that's our initial guess, 50,000. I'm still gonna give you the good one. What about 0? I actually don't know. Ah, there you go. Yeah. See, covariance of parameter could not be estimated. This is basically saying you suck at your initial guess. Okay. Yeah, because it just doesn't fit. I don't know. See, it doesn't give you any fit at all unless you tune it closer to like your initial guess, right? Then you can get a more reasonable value over here. This thing is very sensitive sometimes. If you change it by 1, if it might just go way off. Depending on, it's very model dependent, so you don't really have to get this value. In this case, Planckian is very characteristic. So a wide range of initial guesses work, but in some cases it doesn't. Right? Questions so far? Yes. What?
Oh, wait.
That shouldn't happen. Yeah. Question on curve fit so far? If there's no question, we'll keep going. So how to solve for something? Okay, there's actually an easier way. Okay, there's actually an easier way to find a temperature. There's this thing called Wind's displacement law. Okay, is anyone in Astro 7A? Have you guys learned it already? Wind's displacement law. That's basically relating the wavelengths at which we have the highest temperature to the temperature itself. Sorry, the wavelengths in which we have the highest energy to the temperature itself. And mathematically, that's given by 0.0029 meters times Kelvin. Yes. Divided by temperature, and that gives you the lambda. Okay. And you might be wondering, why am I giving you a number over here? Because this thing cannot be solved analytically. To derive this, you need a computer. To get this number, you need a computer. Okay, but I'm not gonna like derive this number over here, but I'm just gonna tell you that I don't even remember the equation. I did it once, actually twice. Once in my 7A class, once in my 7A class. That equation is this. 5 lambda times the exponential of hc over lambda kt minus 1 minus hc over kt times the exponential of hc over lambda times kt. Yeah, equals 0. Yeah. Yeah, you can actually get this equation analytically. Okay, you don't need a computer. Yeah, but how do we solve it? We have to solve for lambda, right? The way to do this is that I define some equation. Which is over there, right? I can define it. But in this case, we have to define the temperature. Let's just say we use 57,000. That's the surface temperature of the sun. And then we can define some condition equation, which is what that thing is called, lambda condition, right? And what goes in is lambda. This is some parameter that we want to solve for, and then we put that in. Okay, let's put it in. 5 times lambda times, I don't know, like what is that? Numpy exponential times h times c divided by lambda divided by k divided by t minus 1 minus h times c divided by k divided by t times numpy the exponential of h times c divided by lambda divided by k divided by t. All right, there we go. We have the equation. These are just typing. Okay, this is just like speed typing. Like you can spend like 10 minutes doing that typing. That's fine. Don't worry. And now I can solve for find the root because I have a temperature. I know the temperature. What's the maximum? What's the wavelength that emits? Whoa, the most amount of the energy in that star. It's also another way of saying like what's the color of that star because light a different color has different wavelength. And then you can just do import. Okay, import again from SciPy to optimize. Import fsolve, right? And then I just put in this fsolve saying, I'm solving for this equation. My initial guess, give me an initial guess. 12. Fine, maybe it works. Oh, it's not defined. What's going on? What's going on? Oh, there we go. Thank you. See, now it gives you an error. Like, what is a negative wavelength? What is a negative wavelength? Right? We'll put something more reasonable, maybe. Oh, whoa. Let's say 8,000. Is that good enough? Why not? I mean, this is actually not that bad if you're considering the units. This is in centimeters, right? Way off. It's way off. Let's try something else. Maybe I typed this function wrong at some point, but yeah. Yeah.
The accuracy of
I think I typed the function wrong.
starting very close to the thing that it got.
No, sorry. I think I typed the function wrong. Let's come back using this one when I just tried. See, this one works.
Wow. We didn't see that.
Oh, sorry. Yeah, I typed the wrong initial condition. This is the wrong initial condition. Okay, let's say what's the color of the sun? Color.
Yellow.
Yellow. Okay, let's say green. Yellow is around 400 nanometers, which is this thing. This thing. Yeah, there we go. That's why. I don't know why I put that. -7. Sorry, that's nanometers. That gives you nanometers, and then this thing gives you. Sorry, this is centimeters. Gives you your value in centimeters, and if you convert this to nanometers, 5 times 10 to the -5 centimeters is 500 nanometers, which is green, which is the color of the sun. It is. Don't laugh. It is the color of the sun. The sun is the most in a green part of the spectrum. All right. That's it. So any questions? I've shown you all the errors already. Like when you see those kind of unreasonable stuff, please avoid them. And you know how to avoid them now by tuning the initial conditions. Okay. Right. And that's it. If there's no more questions, that's it. Yeah.